Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is In the News. We'll be covering a couple of interesting topics that have found their way into the news recently. And here to talk with us about it is our own Stephen Uitti.
Great to be here.
Good to have you again.
Yeah. So I think we'll see me again too.
I'm sure we will. Now, the first thing we're going to talk about is 3I Atlas. So tell our viewers very briefly just what that is.
So that was a comet. The I in 3I stands for interstellar. So this is the third interstellar object. We had Oumuamua, that was the first, and then Comet Borisov was the second. So these obviously came from outside of the solar system.
Okay, so the first thing we want to talk about with 3I is the fact that they've discovered that it's actively releasing water.
Yeah, so European astronomers, the discovery image was in July 1st. By the end of July, the Swift-Gehrels spacecraft was used, and they got visible and infrared images of it, and they discovered hydroxyl, which is a proxy for water. So it was outgassing water and at 3.5 AU, which is from the sun, which is farther than you normally see for in the solar system comets. But somebody who worked on the TESS project, looking for extrasolar planets, discovered an earlier data and discovered the comet in it in May. So 3 months earlier from that, also found water coming out. And that's just unheard of.
Yeah, at twice the distance that we saw it in July.
Right. So a few things we think are going on there. One is that in order for that to happen, you have to have something outgassing, right? And it's not going to be water because it doesn't sublimate at those temperatures. But carbon monoxide, frozen dry ice. Carbon monoxide could do that, and there's something else as well, and we might get to that. So, so this thing is sort of coming apart. It probably hasn't seen a star before. This is probably the first star it's come from.
Just wandering through the solar system. And
wandering through the galaxy probably for billions of years, and finally came to us.
So, it sounds like it's not a comet that is of our solar system, so where did it come from?
Yeah, so there were 4 articles, or actually 6, that I was looking at, and they used contradictory verbiage. It came from the plane of the solar system, and that generally means that it comes from our part of the Milky Way, which is the thin slice. And these are the younger stars, these like ours, younger like ours, 5 billion years old.
Sure.
Younger, that's astronomy for you. But what we'd really like, is if this thing turned out to be an ancient comet, something from the cosmic noon that we talked about with the James Webb telescope. Has got a bunch of missions that studies on the cosmic noon. 2 to 3 billion years after the start of the universe, which is about 10 billion years ago, 10 or 11. And if we got stuff from then, from this comet, delivered to us, then that gives you comet, this cosmic noon, like in the flesh, ground truth. I mean, that's really exciting.
So something that was not formed along with our sun and our solar system.
That's right, yeah. Predating it by almost 5 billion years, like twice as old as our solar system. And that's what we're hoping, and this weirdness that we get like right away, we're seeing water coming out of it way too soon. It's not from here, certainly, but it's possible that it has a different composition, a very different composition from solar system comets, which we know pretty well these days. So we should be able to recognize that, oh, this is something different.
Yeah, comets that would come from the Kuiper belt or the Oort cloud.
That's right,
Right.
yeah.
Mm-hmm.
So Anyway, so we had an image that was ultraviolet and optical, and in the ultraviolet, apparently they were able to find the hydroxyl. What they were missing is cyanogen, because when you first see a comet in the solar system, you get cyanogen. For one thing, you can. It's not blocked. The signature isn't blocked by the Earth's atmosphere, so you can get it from ground telescopes. Not a problem. But they didn't see any of that at the end of July. But the TESS mission did see it, and they saw it in May. So this compound is buried. It gets blown off because something is turning from solid to gas.
There's some energy source somewhere for it to happen.
And it has to be, yeah. So anyway, so cyanogen is there, and it gets blown off pretty early, right? We could have missed it completely.
So it's quite volatile.
Yeah, but we could have missed it completely because it was before we discovered it. But we happen to have data from a telescope that had the right stuff and happened to be pointing in the right direction, and it was great. And because somebody knew where to look for it, they also got techniques to get it to pop out of the data. Because you look at the data, if you're not looking for it, you're not going to do the right techniques to actually find it. So, so that was another thing. So the other thing that this Niels Gehrels Swift telescope study did was they wanted to get an estimate of the active surface area for this comet, and for the comets that we're used to, you were expecting 3 to 5% of the area of the comet is actively outgassing, and for 3I, for 3I Atlas, it's about 20%. So it's more than 4 times as much of the area, and it's farther out than usual, right? So at 3.5 AU, it's going crazy, right? So this is another sign that this is a comet that hasn't seen a star. It's been in the cold of space for a long time, just for an awful long time.
So, since we know it's not from our solar system, what does this tell us about other solar systems?
Well, to the extent that we can find out what this thing is made of, we can find out what the other solar systems might be made of. It might even tell us something about the progenitor stars that seeded whatever solar system this was from with the kinds of elements and that turned into the dust. You can kind of figure out what that was about. And so we can find out why stars were forming so fast 10 billion years ago. Because the cosmic noon, it was just going crazy. The Milky Way is going crazy. This is the sort of the trajectory out into space, and I'm not sure which way it's going. It might be going to the right. But the dots are color-coded by what kind of a star they are. So these big red ones are actually small M dwarfs. The white ones are F, and the yellow ones are G stars like ours. Right. So if that's us coming at it, we've got some stars that are kind of like our sun, early on, but then a whole bunch of little ones later. They would really like to know where it came from, but all we have is how it came into the solar system. So what people did was they went to Gaia data. So this is astrometry. The location and the speed of stars quite a ways out. The Hipparcos mission years ago was great, but it only goes out to 3,000 light years. The Gaia stuff is a 5-meter telescope, so it's 25 times bigger, and it goes way, way farther. Not just 25 times farther, it's new instruments too, so it goes much better than that. Anyway, so they found 90-something stars, candidate stars, that might have been close to it. They found 62 that were within 2 light years. The trajectory should have gone within 2 light years of these stars. But the closest and the one that did the most course correction or speed correction to the comet produced a negligible impact. So this comet has been sort of going the way it's going, without much
Interference?
but we only go back 4.7 million years in this Gaia data, and that's a long ways. By the way, this most recent, this biggest change happened to be fairly recently. It was 72,000 years ago, right? Well, but like Voyager 1 isn't going to be at Proxima Centauri, which is really close, and this thing is like 80 light years away. So this comet is going way faster than a man-made object so far. Voyager 1 is still the fastest man-made object going out into space.
So you've been talking about like Gaia spacecraft. Will there be any spacecraft that'll be exploring 3I as it passes?
Sure. So there's been talk, and I didn't even go through it, but there's talk about, what would a space mission, if we could just launch a space mission, what would we do? And the answer is, you don't have time to do that. You have to pre-position something out into space and then launch from there, right? It has to be already in space, and you have to be ready to hit the button and tell it to go. But that's not what we're talking about here. What we're talking about here is we have spacecraft all over the solar system.
Yes, we do.
We have New Horizons out at Pluto. I mean, beyond Pluto now, and that's not going to be of a lot of help. So which ones are going to be of help? Well, the trajectory of this comet goes by Mars and Jupiter, and we have 15 active spacecraft at Mars. Not the U.S. The world has,
Right.
So there are a couple of Chinese spacecraft, and there are European and there's even one from India, maybe two now. But in any case, Mars is cool because it's a relatively close approach to Mars, and we have things like MRO, the Mars Reconnaissance Orbiter, which has a super camera for looking at, the thing can let's see, it's about this long. It can spot features that are this big on the surface of Mars, right?
So you're about 1.5 feet between your fingers.
Yeah, it's like 18 inches. In any case, it's a super telescope, right? But you can point that out into space, and so it should be able to get decent images at least. I don't know what other instruments it has, but it should get really good data from wherever it is to a comet, a relatively nearby comet. So so there's also the ESA's Trace Gas Orbiter, which was used to look at Mars's atmosphere. That's got all of the spectrograph stuff that you'd want, I think. But there are two Chinese, Tianwen and Hope, also have opportunities to do this. And so Mars will be in a good spot to see this comet when the comet is closest to the sun. It's perihelion, right?
Okay.
And so it'll be doing the most outgassing and all of that sort of stuff then. But unfortunately, it's going to be on the other side of the sun from Earth. So Earth observatories are going to be, out of luck.
Yeah.
So it's great that we have these things at Mars. But also Jupiter has the JUICE mission. And the JUICE mission will get sort of a ringside seat for perihelion. But also Europa Clipper, which has a magnetometer and plasma instruments. Maybe we could find out it's got a magnetic field. I mean, that would be cool.
That would be interesting.
Anyway, and there are other missions like it turns out that the tail of the comet may in fact have these spacecraft pass through it, right?
Oh, that
so
would
you
be
could
fascinating.
you could actually get really close data if you're ready for it. So Europa Clipper, Hera, and The Lucy mission, which is looking at asteroids, they also may get to go through the tail of the comet. So there are a whole bunch of things. And then finally, SOHO, we have things that are looking at our sun, right?
Right.
Solar Orbiter and the Parker Solar Probe are all going to be looking at the sun. And when you're looking at the sun, you can often see other things going through your field of view. And it turns out that the comet is going to go through the sun's field of view for all three of these instruments. And they've got dates, they've figured out dates for these things. So
Okay.
It's going to be, from late September through mid-November of 2025, so of this year.
All right.
So all of that's cool stuff. Make use of the stuff that you've got already up in space. Given that we're not doing a mission specifically out to 3I, we're going to do pretty good, I think.
Sounds like. It sounds like. As we come up to the break, how could these types of objects help jumpstart planetary formation, do you think?
Yeah, it's kind of weird. So if you do computer simulations of planet forming, when you get to a certain size object, a boulder, maybe it's man size or a person size or 2 or 3 times, it's kind of a big chunk of rock. In the simulations, these things either hit each other and bounce off, and nothing happens, or they hit each other and they both get pulverized. So how the heck do you get past that and build a planet, right?
Right.
And you don't have very much time. In our solar system, Jupiter is thought to have formed in about 200 million years, which sounds like a long time, but it's really not. What they're thinking is that millions of this kind of object should pass through any solar system in the Milky Way in a couple hundred million years. Millions of these things. And so if you have a nice, soft, squishy comet that's already 25, 35 miles across, right, and it goes into the, and they're in the right spot, it could then act as a seed, a planetary seed, and you've gotten past this hard to get past, of boulders hitting each other, and you've got something nice and squishy and big enough gravitationally to just absorb things.
Start pulling things to itself.
Yeah, so once you get that going, then Jupiters are no big deal. and so you get Jupiters in the time that we observed.
Oh.
And so that's the kind of thing that we're looking for. And I thought it was a unique idea. Have people been thinking about this for a long time? Well, this is the 3rd interstellar object, so not that long.
We're going to take a quick break. If you have a question, please send us an email. The address is down there at the bottom of your screen. And we'll be back with our discussion of In the News right after Term of the Month.
Thanks, Don. The term of the month is dust. There's a lot of dust in the universe. What is it? And where does it come from? The universe started out with hydrogen, helium, and not a heck of a lot else. Dust isn't made from these elements. The only thing that stood in your way for seeing at the beginning of the universe was free electrons. But these days, there are huge dust clouds. Looking through an edge of the Milky Way, you can't see very many galaxies. It's because you need an infrared telescope to see through the dust. And for the most part, you need to be in orbit for that. It turns out that Herbig-Haro objects spit out quite a bit of dust, like this thing. So there's a jet at the top, for example. When you add it up, though, it's not nearly enough. And then planetary nebula, like the Ring Nebula, are also not nearly enough. The real cause is core collapse supernovae. They dominate as a source of dust. 0.42, 42% of the mass of our sun per supernova is emitted as dust. Not even the vacuum of space can clean up that much dust. There's the remnant. Here's the remnant of one. Spectroscopy gives us the elements and sometimes molecules that it's made from. And then we have the Crab Nebula, which is also a core collapse supernova remnant. It's recent enough that we can see the dust evolve and figure out what it's made of and find out how much of it is destroyed. About 3/4 of it is destroyed. And that brings the expected total pretty close to what we see. And this was discovered as recently as 2016. So is it the same dust as the dust in your house? Well, sort of. The dust in your house is mostly dead skin and hair. But if we're made of stardust, then it's all the same atoms. And that's the term of the month, dust. Back to you, Don.
Thanks, Stephen. We're back talking about what's in the news. In this segment, we're going to be talking about Mars. Now, Stephen, I understand that the Perseverance rover has spotted potential biosignatures of life on Mars. What are scientists saying about this?
Okay, so first of all, these are somewhat preliminary reports. So Perseverance drills a hole in a rock, it gets some dust and stuff, it does some onboard analysis of it, but it also puts it in a little capsule, and the idea is to leave it somewhere in a cache so that some later mission can pick it up and bring it home so that we could study it in detail back on Earth, because we have better stuff. But so the Mars rover is going along, and they see this thing, and it's got all these little spots in it, and so they drilled samples of it, and they found two pretty interesting things when they did the analysis. And one is vivianite, which contains iron phosphate, and grigite, which is made of iron sulfide. So we have this iron sulfide. The sulfide is important for this, but iron phosphate is phosphorus and like a water OH or something bound to it. But in any case, the interesting thing about these minerals is that they are formed either by life processes, or mainly by life processes on Earth. That's the only way that they're formed. It has been hypothesized that they can be formed with geological processes.
Non-biological.
Non-biological. Mm-hmm. So geological processes, but the material would have to be heated or it would have to be exposed to an extreme acid in order for these things to form. And at least as far as the rover can figure out, with those instruments, neither of those has happened. So we could be scratching our heads thinking of another way to form them. These are pretty new materials for us to be thinking about as biosignatures, but at the moment they're pretty exciting.
I also understand that sulfur gas emissions may have shaped the early climate on Mars, which may tie into this?
Yeah, so the way that the climate has been thought about, generally speaking, by scientists for Mars, it's hard to explain. It's how do you explain what we've got so far, right? But a different group recently did a study, and it was a couple years study, and they said that, hey, sulfur is something that could be spit out of volcanoes, and if it did that early, then you'd get these really good greenhouse gases, and that could have warmed the early Mars, and then we'd have liquid water that we did detect, and we'd have these other things. And so they followed this, following the evidence and following the logic, etc. And so instead of being a water cycle like we have on Earth, we have the changes to how sulfur that happen to sulfur. And one of the things that they predicted, and usually predictions are really explanations of how something that you've found got there, right? So we've
Sure.
got a theory that predicts this, right? They predicted from what they were working on that there should be elemental sulfur that would rain down as sulfur 2, and so you should get this stuff. You should get actually elemental sulfur encased in rocks. This summer, Perseverance rolled over a rock, and when it looked back, it saw elemental sulfur in the rock it rolled over with the wheel.
Oh my!
Anyway, so this is a really good idea. Follow the sulfur, And the idea that sulfur is in one of these two potentially life biosignatures, this is also excellent. So these two studies, which had nothing to do with each other, really do. So then we have the signs of life on Mars. This Planetary Society slide is excellent, and I recommend Googling or using your favorite search engine to look for planetary.org and signs of life on Mars in all one string in a Google search, and you'll get this image as one of the images. You can even use the word image and you'll get this image. And it has the kinds of chemicals that you're looking for. You know, there's 6 of them here, and what a rock looks like, and it's a great slide. And you know, you could study it on pause on YouTube here, but you could also look it up on the Planetary Society's website. That would be great.
All right, well, that sounds great. Steve, I want to thank you for being on this month's show to talk to us about these new news items to inform our viewers. Please visit our club website. The address is down there for you to check that out. And to finish off the show, as always, is What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for October 2025? The sun goes from Virgo to Libra over this month, and we just had the equinox, so days are changing as fast as they do, basically, but they're slowing down as we get to the next solstice. The moon starts with a full moon on October 6th, but we have perigee on October 8th, meaning that the moon is about as big in the sky as it's ever going to be. You might even call it a supermoon. Last quarter is on the 13th, new moon is on the 21st, first quarter is on the 29th. Then we have Mercury and Mars shown on the 1st of October. Mercury goes from Virgo to Scorpius and sets from 2 hours to 0.7 hours, almost an hour, after sunset. And Mars has maximum eastern elongation on the 29th. So it's much better at the end of the month, shown here, of course, at the beginning. Mars goes from Virgo to Libra and sets from an hour to also 0.75 hours, 3/4 of an hour after sunset. And almost everything else is true. Then we have Venus, Jupiter, and Uranus. Venus goes from Leo to Virgo and rises from 2 hours to an hour and a half before sunrise. So this is all morning stuff. Jupiter is in Gemini and rises from 6 to 8 hours before sunrise. And then Uranus is in Taurus and rises 2 hours after sunset. So it just happens to be on the same screen. To an hour after sunset. And they're all best at the beginning of the month. Then we have Neptune, Saturn, and Pluto. Saturn is in Aquarius and sets from an hour to 3 hours after before sunrise. So it sets before sunrise. That's interesting. Neptune is in Pisces and sets from an hour to 4 hours before sunrise. And Pluto is in Capricornus and sets from just after midnight to just before midnight. It's better earlier on in the month just because we're closer to the opposition, which was in July. This might be the last month where Pluto is fairly easy as Pluto goes. You know, for all of this stuff, dress warm. That's what's up in the night sky for October 2025. Remember, we don't charge money for this show, but we may tax your brain.